Good afternoon, everyone. I'm Jimmy Chen from University of Bristol, and I'm supervised by Robert Sala and Yanni Badeni. So today I'm gonna talk about the Painlevè paradox that results from the indeterminacy in rigid body friction model, and how I'm gonna to try to resolve it by taking into account more physics, in particular wave models. So the Painlevè paradox causes instability phenomena in robotic systems, such as the undesirable hopping motion in robotic arms, or just in everyday life when you pushing a chalk on a blackboard or pushing your fingers on a rough table, the bouncing it generates, the phenomenon it generates. So we are interested in studying the this phenomena. So the Painlevè paradox can be demonstrated by the configuration so-called classical Painlevè problem, which consists of falling rigid slim rod in contact with a rigid frictional horizontal surface. When the rod is in contact with the surface, the tangential and normal contact forces F and Ft are acting at the contact point P. From the equations of motion about the center of mass G, we can derive the normal acceleration of the contact point when the rod is sliding to the left, which we call the negative slip, in terms of parameters B and P. If we look at the signs of these parameters, when they are both negative, if it's in contact, the normal acceleration is negative, pushing the rod into the surface, which is impossible. So the rod has to lift off. In that case, the normal acceleration is still negative, which takes it back into contact with the surface, which is also impossible. So there is actually no possible continuation in this case, which is called inconsistent. If B is positive and P is negative, if there's no contact force, the normal acceleration is positive and the rod just lifts off. If it's in contact, the normal contact force is minus B/2. So in this case, we have two possible continuations, which is indeterminate. And this inconsistency and indeterminacy are what is called a Painlevè paradox. You can see that the paradox occurs when the parameter B is negative. If the rod is uniform, the coefficient of friction is actually greater than 4/3, which may seem unrealistically large, but it can actually be much smaller if we reduce the radius of gyration by making the mass more concentrated at the center of mass. The left figure is the phase portrait of the angle theta and the angular velocity omega. The paradox region is the yellow and brown region between some angles. It has been shown that the trajectories can only get into the paradox region via the top left singular point. If we look closer at the singular point, the dynamics around the singular points of parameters P and B, you can see that it is actually only when the coefficient of friction is greater than a critical value, there exists a region of initial values that can reach the paradox region through the specific singular points. Otherwise, it would just pass B equals 0 and the rod lifts off. So the paradox shows the limitation of the rigid body formalism. So what I'm doing is try to taking into account extra physics by introducing transverse and longitudinal wave models. When the rigid body hits the surface, there is a jump in acceleration, and the entire body feels the effect immediately. But in our model, that the continuum elastic body has a jump in velocity at the contact point, and it propagates through the rod with finite speed. For the transverse wave model, the Euler beam model cannot capture the jump at the hitting moment. So I use the Timoshenko beam model, wave model. And this is the system of the waves in the frame of the falling rod, and the applied forces acting perpendicular to and along the rod on the boundary conditions. The idea to solve this system is to first compute the equilibrium shapes when the forces are applied, and then use it as an initial condition to calculate the wave solution on top of it. And by the linearity of the wave systems, we can just add them together to obtain the solutions, and then use this solution, we can derive a new system of motion and determine the conditions for switching. Once we have the equilibrium shapes, which is proportional to the contact forces, we can use this, we can add the perturbation and use this solution form, substitute it back to the systems of way to obtain the dynamics of the perturbations. And we actually only need the first and second type derivatives of the solution at the contact point. The solution can be written in integral forms by Duhamel principle, and by integration by parts twice, we have this form here with the remaining integrals, which can be defined as new variables, which are memories of the forces. The WH in it is the solution to the homogeneous system, which can be solved numerically by using spectral methods to turn it into a system of ODEs, and then introducing damping. The numerical solutions can then be approximated by a simple function form here. And with these two additional variables, we can extend the system of motion of the rigid body. And the contact force depends on which mode of motion is in. They can either be a free fall, stick, or positive or negative slip. And next, we need to determine the conditions for switching. And the conditions for switching between contact modes and transiting out of contact into free fall are simple. The hardest part is to determine the switching from free fall when the rod hits the surface, because there is a jump in velocities and forces. So their first order time derivatives are unbounded. We handle this unboundedness by first defining the time just before contact by Tc minus, and the time just after contact by Tc plus. And then we integrate the accelerations between this time to obtain the relations of the variables before and after. And with some newly defined variables, we can actually determine unique solution, unique conditions for switching from contact modes to freeform. And I did some simulation and compare them with the compliant contact model, which we released the constraint of rigid contact. You can also think of it as adding a spring at the contact point. And these are simulations of the velocities, and our model can capture the vibrations of it. In summary, we consider exophysics, physics, and the two additional degrees of freedom can hopefully help to resolve the paradox that occurs in the rigid body models. And we have also determined the unique conditions for switching from free fall to contact. In the future, plan is try to use this new model to analyze the behavior of the dynamic jump. And in the future, hopefully I can extend the numerical solvers by incorporating this model into more complicated engineering structures like a joint or anything. Because usually the numerical solvers like finite element method tend to avoid jumps.